All right, this is on the properties of roots of polynomial equations and the fundamental theorem of algebra. You can go ahead and pause and read. The big thing that I want you to highlight on this slide is if a polynomial is degree n, so like a third degree polynomial, then counting the multiple roots separately has that many roots. So if I have a third degree polynomial, you're going to have up to 3 roots. Some of the roots can be complex, and if that's the case, you have to take its conjugate, would be the other root. This next slide is on the linear factorization theorem. It shows that if you have a polynomial in general form and you can factor it into separate factors. So there's an example below. Here is a 4th degree polynomial, and they found 2 complex numbers right here. Those are the conjugates. And then they give you one more of 2. There must also be another 0 at 2 because it has a repeated root. So this is what it would look like in factored form. All right, what we're going to do is we're going to go to this first example. It says find a 4th degree polynomial function with real coefficients that has -2, 2, and 0, or I as zeros, and that when we evaluate the function of 3, we output -150. So since this is a complex number, you're going to have another 0 at its conjugate, x equals -I. Because complex numbers occur in pairs with their conjugates. So we're going to go ahead and write this in factored form. So in the yellow box, I just put your linear factorization theorem. The degree is 4. X, and now I'm going to take care of this first one, -2, so write that in factored form. It's the opposite sign, +2. The next one is opposite sign. The next one. And then the last one. And then we have this guy here, f of 3 equals -150. So that'll come in a little bit. So I don't know what that leading coefficient is, so I'm just going to go ahead and put a sub n. We will find that later. So now we're going to multiply these binomials together. And how we do that is by the FOIL method. So first, outside, there should be a minus there. Inside, and last. One more time. First, outside, inside, last. Now I'm going to simplify those brackets. So I'm going to combine like terms. And that -I squared replaces with a -1, so -1 is a +1. Now we have to FOIL again. First, outside, inside, last. Combine your middle terms. All right, so now we have this polynomial in general form, and we need to find that leading coefficient. So, how we find that leading coefficient is we start to work with that f of 3 equaling negative 150. So f of 3 equals 150. So if I substitute 3 in for x, I should get it to equal 150. So I'm going to set that f of 3 equal to 150. Now I'm simplifying this bracket. So 3 to the 4th is 81, minus 3, 2 squared is 4, minus 4. And now if you're comfortable, just go ahead and take out your calculator. That bracket will become 50 a sub n. One thing I just noticed here, this is a negative. So this should be a negative and a negative. Now we solve this for a sub n. A sub n equals negative 150 over 50. So that leading coefficient is negative 3. So now, if we go up to the top, right here, that's what we're looking for, that a sub n. That a sub n, that leading coefficient, is negative 3. We're going to put it right there. So f of x equals negative 3 quantity x to the 4th minus 3x squared minus 4. And then you just distribute that negative 3. And there is your polynomial function that is a degree of 4. I did show you graphically what it would look like. Here are the two x-intercepts that are real. The other two zeros are complex, so they will not be x-intercepts. If you wanted to trace along the curve of f of 3, so let's say here's on the x-axis 3, this ordered pair would be down here at over 3 down 150. That would be an ordered pair on the graph.